Hello, chemists. This is Ms. Placino, and you are watching Screencast 9.6 on entropy. Entropy is kind of a cool topic to talk about and think about, and what we're going to do today is investigate the role that it plays in chemical reactions. So I want to talk about the second law of thermodynamics to get us started. A nice clean room. Think about how long it takes you to clean your room, or clean any room really for that matter. I know that some of you may have never actually been able to successfully clean your room. There's just so much stuff in it. But if you really think about it, the last time you did a good job cleaning your room, it probably took a while. You had to go through and make your bed and put away your clothes and get everything back to a certain spot. How long does it take you to mess up your room? If you're like most people, you don't even have to try, and it just kind of happens. I know I get home from school, and by the time I've taken off my shoes and I take off my jacket and I put my backpack down, it looks like, something exploded in my living room. It just happens without me even really noticing it. It doesn't take any effort. It just seems to naturally become messy. And that's what the second law of thermodynamics is all about. We have what are called spontaneous reactions. And the second law of thermodynamics states that the universe is constantly becoming more disordered. If you want to take that disorder and organize it, it requires energy. And it seems like things get messed up on their own in virtually no time at all. But in order to reorganize things, you have to burn energy. It's going to burn through calories as you're making your bed and folding your laundry and dusting and putting things away. So second law, again, it states that the disorder or the entropy of the universe is always increasing. And try to use this as an excuse not to clean your room. Tell your parents you're breaking the second law of thermodynamics and you're just really not comfortable with that at this point in time. See how that goes over. Entropy, and in thermochemistry, entropy is represented by S. Entropy is just a measure of the degree of randomness of the particles in a system. So if you were to think about any piece of matter and imagine you're shrunk down so small that you can see the individual atoms or molecules, or just generally speaking particles that make up that substance, how ordered or disordered are they? If you have a large degree of randomness, you're going to see very large entropy numbers, large positive numbers. If you are not very random, or you're pretty organized, a very small degree of randomness, you're going to see small entropy values. So we're going to be looking at what happens to the disorganization or the randomness of the molecules as you move from reactants to products, whether we're talking about physical changes or chemical changes. If the products are less disorganized, they are less random, we'll have a change in entropy or a delta S that is negative. Excuse me. If the products are more disorganized, or they are now more randomized, we're going to see a positive delta S. Positive delta S's, changes that increase the disorder or increase the randomness, increase the entropy, are what we call energetically favorable. All that means is that they release energy. Anything that requires or absorbs energy is energetically unfavorable. Again, it doesn't mean it can't happen, it just means that energy is required. So most systems in nature are trying to move to a more randomized, more disordered state. So we're going to talk about a handful of ways to change entropy and really trying to evaluate that as this change occurred, has the entropy of the system increased or decreased? So when matter changes phases, entropy has changed. We've got solids, liquids, and gases. Hopefully you know by looking at that your gas is going to have your highest degree of entropy, the most entropic. Liquids in the middle somewhere, and solids are going to be the least entropic. So again, low entropy for solids, high entropy for gas. Solids are very organized, gases are very random, so they have high entropies. This can also work for chemical reactions as well. If you take something like calcium carbonate or chalk, given enough time and the right conditions, you can form calcium oxide and CO2. which is a gas. So in a chemical reaction, you can decide if entropy has increased or decreased by looking at the phases. So I've got a solid a solid, and a gas. We know that gases are the most entropic, so I started off with just a solid. I was able to produce a solid and, more importantly, a gas as the reaction progressed. So this represents an increase in entropy. Anytime you make a solution, you have increased the entropy of a system. If you think about it, a solution is a mixture usually of two substances, one of them being water. You have two pure substances as water, and in this example, salt. If you mix them together, the particles are going to mix. It's going to become more random, and you're going to increase entropy. If you're able to see it on the molecular level, it's even more interesting than that, because the water molecules are able to rip apart the sodium and chloride ions, solvate them, and you have even more disorder than you might have expected with just something like a non-electrolyte. Entropy and temperature. If you have the same substance but at two different temperatures, even if they're in the same phase, as you might imagine, the substance that's at a higher temperature is going to have a greater degree of disorder. Think about what's happening to the particles of a substance as you heat it up. The molecules get moving around a lot faster. They're going to be bouncing off each other with more force. Therefore, we have this direct relationship. As you increase kinetic energy, or you increase temperature, you're going to see an increase in disorder. Pressure can also affect entropy. If we've got this example here, both cases we're dealing with a gas. They're under two different pressures. As pressure increases, and this is our increase in pressure, you can see that the particles get forced closer together, so they're not quite as random as they were before. So we see an indirect relationship. As you force the molecules closer together, you tend to see a decrease in disorder or a decrease in entropy. It's worth pointing out that this really applies to gases only. With solids and liquids, the particles are already pretty compressed, so trying to press on it even more is going to have no noticeable impact. Finally, you can look at entropy in moles. So if there are more moles of products than there are moles of reactants, it's likely the entropy has increased. This is kind of a last-ditch resort. This is not the first thing you want to look at when you go to evaluate the entropy change of a system. This should just be, well, I can't figure it out from anything else, so I will resort to this. If you look, we have CH4, H2O, CO, and H2. In every single case, we're talking about gases. So I've got two gases as reactants, two gases as products. I'm not going to know if that's an increase or a decrease in entropy there. I don't have any information about the temperature or pressure changes that occur as the reaction occurs, so I can't make any judgment there. I'm kind of left just comparing number of moles. So if I add up the coefficients, 1 plus 1, math I can handle, that's 2. 1 plus 3, that equals 4. 4 is greater than 2, therefore as the reaction progressed, it's most likely the entropy has increased. And again, this is really a last resort. It's not as reliable as the other methods, but in a pinch you can use it, and oftentimes it will work out. This is the worst way to do it. So let's try some practice. I want you just to tell me if the entropy increases or decreases and support your answer. So there they are. So I'll give you a chance to brainstorm about those, maybe write them down into your notes, and we'll come back and talk in just a few moments. All right, so let's start off with question number 1. We have water vapor turning into liquid water. This definitely sounds like a negative delta S. A liquid is going to be more organized than a gas, so this is a decrease in entropy. We've got 2NO2 going to N2O4. They're both gases. I don't have temperature or pressure information. I'm going to have to go with last ditch resort, which is compare the number of moles. I went from 2 down to 1, so there's a good likelihood, oh no, sorry, that this is going to be a negative change in entropy as well. Water is heated from 25 degrees Celsius to 50 degrees Celsius. That's going to increase entropy. As the water molecules move around faster, there's going to be more disorder. I've got barium chloride and I dissolve it in water. Oh, this is making a solution. That is an increase in entropy. N2 plus H2 gives me NH3. I've got all gases, but I've got 2 gases on the reactant side. I only have 1 gas on the product side. I could probably try to compare moles here too. 4 moles of reactants versus 2 moles of products. This sounds like it's going to be a decrease in entropy. And finally, I'm going to take C6H6, most likely benzene. I'm going to light it on fire, react it with oxygen to form carbon dioxide and water vapor. I have a liquid on the reactant side. I've got gases only on the product side. I would think this is going to be an increase in entropy. A little bit later this unit, you'll learn how to calculate entropy values in exactly the same way you calculated enthalpy, delta H values. Okay, just a little bit more about entropy before we wrap up. Sometimes you won't be looking at a change. You'll just have 2 substances that you have to compare. And it's easy if you're talking about a gas versus a liquid, or if you've got information about the temperature of 2 substances or the pressure of 2 different gases. But sometimes you're just given something like this, where you're asked to compare, let's see, this is helium and 36 and krypton. If they're under the same temperature and pressure conditions, at first glance you might think, well, it's basically impossible to try to figure out which one is going to be more entropic or have a greater degree of entropy. With these Bohr model diagrams, I'm trying to give you a hint at what you can look at. If you're thinking electrons, you're on the right path. Something like helium just has 2 electrons. We know the protons and neutrons are pretty much captive in the nucleus. Nothing much is going to happen there unless you have a nuclear change. So just those electrons are going to be moving around. Same thing with krypton. The protons and neutrons in the nucleus don't go anywhere, but now we have 36 electrons that are going to be zipping all over the place. It turns out that larger atoms and molecules tend to have a greater entropy than smaller ones. With individual atoms, we're talking about electrons. When you think about molecules, I know we haven't really discussed it yet. It's more of an advanced topic, but those bonds are not static. The atoms in a molecule are vibrating. There's bending, there's stretching, there's contracting, there's all sorts of motion. So if you have a larger molecule or a larger atom, they tend to have a greater entropy than smaller ones. Okay, I guess that definitely wraps it up for today. There are a handful of practice problems in your notebook. Try those out and check your answers online. I hope you found this helpful, and I will talk to you again soon.